Since we're diving into polynomials, we need to take a deep dive into how to find the zeros of a polynomial function. Today's lesson is going to focus on the real zeros of these polynomial functions, and our next lesson will talk about most of the complex zeros of a polynomial function. So before we really begin this in earnest, we need to review some division rules. So vocabulary-wise, when we're talking about division, please remember that the dividend is the thing that you're dividing into. The divisor is what you're dividing by, and you would get the answer, which is called the quotient. And if there's a remainder, you put that remainder over the divisor. So in case you forgot, let's talk about long division for just something simple like this. Long division, if you think back to elementary school, would look something like this. The steps for division are divide, multiply, subtract, bring down, and repeat. Now, if we were to divide 5 by 6, that doesn't work, right? So we scoot over one place unit, and we divide 53 by 6. And 53 is divisible by 6 8 times. 8 times 6, that's the multiply step, is 48. We subtract that number, we would get 5, and then we bring down whatever's left of the number. Repeat. 58 divided by 6 would be at most 7. 7 times 6 is 56. We subtract, and there's nothing left to bring down, so this has become our remainder of 2. Now, the way we would write this is 87, that's my quotient, with a remainder of 2 over my divisor, which is 6, or 1/3. Obviously, we could reduce that fraction. But that idea is going to help us translate into long division of these polynomials. So again, remember, the steps are divide, multiply, subtract, bring down, and repeat. But I want you to make a little note for yourself that when we're talking about subtracting, we're talking about adding the opposite. Okay, so make sure you're actually subtracting, which means you're adding the opposite. We're going to set up this division problem the same way we would have set up a division problem for regular numbers, which means my dividend goes on the outside of the little fraction bar or divisor box, and your dividend goes inside. One thing we have to make sure that we do is that we leave a placeholder for all of the terms. So if you notice that we've gone from power 4 to power 3, the next one would be power 2, but we don't have any squared terms, so we're going to leave a 0x squared plus 5x minus 1. Okay, so we follow the steps: divide, multiply, subtract, bring down. Now you can't divide a two-termed polynomial, a binomial, into just a monomial, just one term. So just like before, we're going to scoot over and we're going to start listing out our quotient here. Okay, so we divide 2x to the 4th power divided by just x would be 2x cubed. Okay, so then we multiply, but we're going to be multiplying by both pieces. So 2x cubed times x is 2x to the 4th. Those should always match, that's what we want. And then 2x times -2 is -4x cubed. Now don't forget, we are subtracting that whole thing, which means we are adding the opposite. The first ones would cancel out, and if we add the opposite, so we're subtracting a negative, which means we're adding, we're actually going to end up with positive x squared. I'll put a 1 there just so you can see it. Not squared, cubed. 1x cubed. Okay, we've divided, we've multiplied, we subtract, we bring down. Now, I bring down everything so that I'm working with the correct polynomial every time. And then we repeat. This time, we're going to be doing 1x cubed, the first term here, divided by that first part of our divisor. So 1x cubed divided by x, that is x squared. And then we multiply. X squared times x is x cubed. X squared times -2 is -2x squared. Subtract. The first terms should cancel, and you're adding the opposite. That's 2x squared, bring down, plus 5x minus 1. Repeat. 2x squared, the new front term, the new leading coefficient, and that's what you can call this, divided by x, is positive 2x. Positive 2x times x is 2x squared. 2x times -2 is -4x. Again, we're subtracting. These would cancel, and I'm adding the opposite, so that means I have 9x. Bring down. Repeat. 9x divided by x is 9. 9 times x is 9x, and 9 times negative 2 is negative 18. But remember, we're subtracting, which means we're adding the opposite. Negative 1 plus 18 is 17. So now we have our remainder, because there's nothing else to bring down. That means that our final polynomial quotient is 2x cubed plus x squared plus 2x plus 9 plus 17 over the divisor of x minus 2. And that's long division. Now there's another method of division that you can use, but you can only use it when you're dividing by a term that is a binomial and that has a power or degree of 1. So it looks something like this, x minus c or x plus c, because you need to be able to have a c value, and that's called synthetic division. So very quickly, when we're setting up synthetic division, it looks a little bit different. You're going to put that c value on the outside of, like, I don't know, I call it an upside down division box. And you're going to list out only the coefficients, still in standard form, which means you put zeros for missing terms. And you're going to follow the pattern until you're done. That stands for bring down, multiply, add, multiply, add, multiply, add until you're done. And when you finished, you're going to get a bunch of different terms that start on the right side with your remainder, then your constant, then your x, and then your x squared term, and on that direction until you fill out all the terms. So hopefully you notice we're actually using the same polynomials here as the first one. So we already know what our answer should be because we found it using long division. Let's set this up. So we have our upside down synthetic division box. Our c value is 2 because x minus c, so x minus 2, that means c is 2. And we're going to list out just the coefficients. 2, negative 3, 0, 5, and negative 1. Means that we bring down, and then we multiply. 2 times 2 is 4. Then we add straight down. Negative 3 plus 4 is 1. Then we multiply. 2 times 1 is 2. Add. Multiply. Add. Multiply. Add. So that we end up with a remainder of 17, a constant term of 9, an x term with 2, an x squared term of 1, and an x cubed term of 2. So if I put that all together, this would be 2x cubed plus 1x squared plus 2x plus 9 plus 17 over x minus 2, which again is exactly what we got when we did this with long division. So synthetic division, one, saves us paper, but is another way that we can divide these polynomials, but only if the term we're dividing by looks like this. So x minus c or x plus c. Okay, one more thing I want you to notice, and again, hopefully you notice that this f of x term, this polynomial here is still the same, the numerator or the dividend that we've been using on this entire page. This example says evaluate f of 2. So, okay, well, we know how to evaluate functions. F of 2 is just like saying 2 times 2 to the 4th power minus 3 times 2 to the 3rd power plus 5 times 2 minus 1, which is just like saying 2 to the 4th power, that's 16 times 2 is 32. 3 times 2 cubed is 8, times 3 is 24. 5 plus 2 is 10, minus 1. So when you do all of that math together, you end up getting 17. What do you now notice? Hopefully you're like, wait a second, wasn't that the remainder? And that's exactly true. We actually have an entire theorem for this. It's called the remainder theorem. If a polynomial is divided by some factor x minus c, then the remainder is the same as the function value f of c. So if we're just trying to figure out the remainder for some division problem, instead of doing the entire division problem, we can use this remainder theorem to find the remainder if we just evaluate the function at that particular c value, just like we did up here. Pretty dang cool. So what this means for us is when a polynomial is divided by some factor that looks like this, x minus c or x plus c, we can find the remainder in three ways. We can find the remainder using long division. We can find the remainder using synthetic division. Or we can find the remainder using the remainder theorem. Which again is just evaluating f of c. You get to pick the version of these that you use. You probably don't want to choose long division since it's so long, but all three of those are valid ways that you can find the remainder when we're dealing with polynomials, which is pretty cool. Okay, so a couple more pieces of information we need to know. When we divide two numbers and the remainder is 0, just think about regular numbers, then the value we divided by as well as the quotient are called factors. And you know this fact. So if you were to take 20 and divide it by 5, the remainder would be 0. So we call 5 a factor of 20, and the quotient, 4, is also a factor of 20. Like, that makes sense to us. The same thing works for polynomials. So therefore, if a polynomial is divided by some factor and the remainder is 0, then that factor is an actual factor of the polynomial, and the answer obtained from the division is also a factor of that polynomial. And this is told to us in another theorem. This is called the factor theorem. Here's another theorem we need to probably look at and memorize. It says for a polynomial function, x equal to c is a 0 if and only if x minus c is a factor of the function. So we need to prove that some x minus c is a factor to be able to say that that value c is also a 0, which is our end goal of this lesson, to talk about the zeros of polynomials. Now, due to all these facts and the way that all of these things are related, all of the division, the factors, the roots, the zeros, we know the following three statements are equivalent. The value c, x equals c, is called a solution or a root of the equation f of x when it's set equal to 0. What's equivalent to that would say the same thing. When f of x is divided by x minus c, the remainder equals to 0, which means c is x minus c is a factor, which then means that c is a 0 of the function and that c is an x-intercept of the graph of f of x, given that c is a real number, like not an imaginary one, and also that x minus c is a factor of f of x. All 5 of those statements are equivalent, so it allows us to relate graphs to equations, to zeros, to remainders, to all of this stuff together. So let's talk about what that means in not a theoretical situation. So we're given the information that x equal 5 is a 0 of the function, and we want to write 4 equivalent statements. So we're told that 5 is a 0 of the function. So another statement we can make is that x equal 5 is a solution or root of the equation f of x equal to 0. We can also say when f of x is divided by x minus 5, that factor, x minus c, right? The remainder is going to be 0. A third statement we can say that's equivalent is that 5 is an x-intercept of the graph of f of x, because 5 is a real number, so we can say that. And the last statement we can say is that x minus 5 is officially a factor of f of x. We know all of this just by knowing that x equals 5 is a 0 of the function. So knowing the zeros of your function is huge to be able to talk about a lot of other important pieces of a polynomial. One of the building blocks and the reasons why we use this factor theorem is because it allowed us to determine whether polynomials have certain factors. And we're going to talk about why we would use different numbers later on in this lesson. But if we say we're trying to figure out if x minus 1 is a factor of this polynomial given, what we need to do is focus in on that c value. So x minus 1 means that the c value is positive 1. And the factor theorem tells me that all of these different things, if the remainder is 0, if all of these things happen, then that is a factor. So I'm going to check and see if the remainder is 0 using synthetic division. So synthetic division, you have your c value on the outside and just the coefficients of that term, of that polynomial, and we bring down and then multiply, add. So 1 times 2 is 2, negative 1 plus 2 is 1, 1 times 1 is 1, 2 plus 3, 2 plus 1 is 3, 1 times 3 is 3, negative 3 plus 3 is 0, which means that, our remainder is 0. We'd have the constant, the x, and the x squared. But this is really what we're looking for. If your remainder is 0, then it's a factor. So let's write that in a little mathematical sentence. So therefore, x minus 1 is a factor of f of x because when we divide f of x by that factor x minus 1, the remainder is 0. Voila. We have determined that, yes, x minus 1 is a factor because our remainder is 0. It's our factor theorem. Okay, let's try the next one. If we're trying to check if x plus 2 is a factor, that means our c that we're checking, our 0, would be negative 2. So let's set up our synthetic division to check, again, the c on the outside and just the coefficients from that polynomial on the inside. We bring down and then multiply, add, back and forth with this pattern over and over again. Multiply, add, multiply, add, and because our remainder this time is not 0, that is not going to be a factor. So let's write that in a math sentence. Therefore, x plus 2 is not a factor of f of x because when the function f of x is divided by that factor x plus 2, the remainder is not 0. So this remainder theorem is going to help us knock out some examples or choose the correct c values, the zeros, so that we can factor polynomials that are of these higher degrees. Okay, let's lead ourselves there a little bit. If we look at this example 6 here, it says to completely factor this polynomial. This polynomial is degree 3, so we should have 3 zeros. Okay, we get a little bit of a hint from this graph. Since this graph has 3 zeros, it has 3 x-intercepts, you have an x-intercept here, here, and here. I have no idea what this one is because it's in the middle of 2 points, but this is negative 2 and this one's 1. So I know what values I'm going to divide by to begin with so that I can find out what that missing term is. And we're going to do that using synthetic division. So I'm just going to start with negative 2 and set up my synthetic division. 3, 4, negative 5, negative 2 are my coefficients. I bring down, I multiply, I add, I multiply, I add, I multiply, I add. We know we should get a remainder of 0 since visually this is a 0 on the graph. But I'm not necessarily done because I still want to be able to check the next one. We know that there's going to be a 0 at 1 from the graph, the x-intercept. So we go ahead and do synthetic division again. Bring down, multiply, add, multiply, add. Again, we knew this should have been a remainder of 0 because we see it on the graph. So here's our remainder, this is our constant, this is just an x term. Which means that my polynomial is going to completely factor to x plus 2, x minus 1, and 3x plus 1. Where did I get all those things from? Good question. The first c value, the second c value, the third factor. And that makes sense because negative 1/3 would be the way you solve this little factor for 0, and that's about negative 1/3, so that checks out to me. But we're not always provided with a graph. So there are times we have to go straight from polynomials to the zeros instead of having a graph. One of the ways we're going to be able to do that is with this rational zeros theorem. It says, for any polynomial f of x with integral coefficients, the only possible rational zeros of f of x are of the pattern plus or minus p divided by q, where p is a divisor of the constant term and q is a divisor of the leading coefficient. So in this first example, p would be 6 and q would be 2. I'm not really worried about signs because we're going to have plus or minus. So what I do for this sort of problem is I say, okay, p is 6, and here are all the factors of 6, 1 times 6 and 2 times 3. And here's q is 2, and all the factors of 2 are 1 and 2, which means we start combining these into all of our potential rational zeros. We make a list. Okay, so p over q, we're going to have 1 over 1, which is 1. We're going to have 2 over 1, which is 2. We're going to have 3 over 1 and 6 over 1. Then we're also going to have 1 over 2, then 2 over 2, then 3 over 2, and then 6 over 2. Now, hopefully you're thinking, well, Miss Quigley, isn't 2 over 2 just reduced to 1? And it does, so we don't need to list that again. And then, also 6 divided by 2 reduces to 3, and that's already on my list. So I actually don't need those 2 on my list. So let's clean this up a little bit. You can just mark them off, but just for housekeeping, I'm just going to make this all nice and pretty. So here's my nice final list of all of the possible numbers that could be zeros for my function. Now, here's a problem. That's a lot of things to try, because that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different potential numbers that could be zeros for this function. So what we're going to do is we're going to cut down the numbers that we need to try very quickly using our graphing calculator. Now, unfortunately, as I've said before, I don't have a way to show you the graphing calculator on here, but I'm going to link a video in the description where another teacher from Mesquite ISD shows the steps. But basically, what we're going to do on this problem, and I'll write down the steps for you, I just can't show you. We know that this is a degree 3 polynomial. Therefore, we need to find 3 zeros. Always good to know that. What you're going to do in your calculator, so your TI calculator, is you're going to press second and then table set. And you're going to change the independent value from auto to ask. So you just go select ask. And what that does is it gives you an empty x and y table when you go to your table. And you can actually put in the numbers you want to try in your x-axis. So we're going to try all of the numbers in our potential rational zeros list. And we're looking for that number to equal 0. Okay? So you type this function f of x into your y equals. You go change your table settings so that you can try plus 1 minus 1, plus 2 minus 2, plus 3 minus 3, plus 6 minus 6, plus 1 half, negative 1 half, 3 halves, and negative 3 halves. And when you test all 12 of those options, there are 3 that are going to show up with equals to 0, that the table gives you the number and then 0. So again, what it would look like is like 1 and 0, or negative 6 and 0. or negative 1/2, and 0, which is exactly the number. So we would say 1, negative 6, I like to circle them up here, and then negative 1/2. So my zeros, using the calculator to eliminate options off of my potential rational zeros, we know that the solutions are 1, 6, and negative 1/2. Sorry, negative 6. Those are my zeros, which means the factored version of f of x is just the factors using those zeros. So x minus 1, x plus 6, and 2x plus 1. The factors. We have our zeros, and we have our factored form. Again, really sorry I can't show you. I don't have that capability on this recording thing. But again, if you want to see that in real time, I will put the link to a video where it does show you how to do this in your calculator in the description of this video. So you can click over to that. All right, so here's the big kahuna here. Starting from this polynomial, we just want to find all of the zeros of it and write it in factored form. Couple things to notice before we get started. This is a degree 5 polynomial, which means we know there are going to be 5 zeros. All right, we know this. Okay, let's do the p and the q thing. Remember, p is the last number and q is the leading coefficient, which in this case is 1. So all of the factors of 36 are, buckle up, 1 times 36, 2 times 18, 3 times 12, 4 times 9, and 6 times 6, but nice enough, q is 1, so the only factors of 1 are 1 and 1, which means my list of potential rational zeros is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 9, plus or minus 12, over 1, right? I'm doing all of these over 1 in my head, and plus or minus 36. Woo, that's a lot of numbers we could have been dividing by to see if they come out to nice rational numbers. So instead, we're going to use that calculator tool with the ask. We're going to type in the entire function into y equals and then test out all of these potential rational zeros. Now when you do that, and pause this video and try it, you should be able to notice that when you type in 1 on that table, it comes out with a y value of 0. And you'd eliminate a whole bunch, and when you come out with a factor of 3, it also would be partnered with 0. So we know that our zeros from this table, from my calculator, are 1 and 3. Okay, let's start doing some synthetic division to see where we end up after that. So let's do 1 divided into 1x to the 5th minus 7x to the 4th plus 19 x to the 3rd minus 37x squared plus 60x minus 36. Oop, didn't make my thing long enough. Okay, bring down, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. Whew, remainder 0, that's what we wanted. Our next 0 was 3, so again, repeat. Bring down, multiply, add, multiply, add, multiply, add, multiply, add. Again, we know that that should have been a factor. One of the things we're going to talk about next class is the number of complex and the number of real, so real and non-real zeros that a graph should have. I'm just going to feed this one to you a little bit here because it's a little bit more than we need. We should have another real solution. And we only found 2 of them up here, which means one of these is going to be a repeated root. And you could check on a graph to see which one of these bounces off. Remember, we talked about this last time, that a repeated root is going to bounce off the x-axis instead of going through it. So you could always graph this to check it. Or try synthetic division again. So just because we're on a roll, let's try synthetic division with 3. Bring down, multiply, add, multiply, add, multiply, add, and thank goodness we tried 3. I wonder why I picked 3. That would mean it's also a factor because the remainder is 0. Had you tried 1 again, it wouldn't have worked. You would have gotten a remainder that was non-zero, and you would have known that that wasn't one of your factors. Okay, which means now that we have these 3 factors that are real, we'd be able to use this leftover piece right here, our quotient, as our very last part of this function. So let's put it all together in factored form. You'd have x minus 1, x minus 3 twice, multiplicity 2, and then x squared plus 0x plus 4 as the last part. That's called an irreducible quadratic factor, which again we will talk about next class. So I gave you a little bit of a preview of something we're going to talk about next class. No big deal, because you can always graph these things to see if it bounces off or goes through. And if it bounces off, remember it's an even multiplicity, so we knew that had to be 2. We talked about the intermediate value theorem last class, so let's apply that to polynomials here. Let polynomial f denote a polynomial function if a is less than b, and if f of a and f of b are of opposite signs. So when we evaluate at a and we evaluate at b for the polynomial, one is negative and one is positive, then there is at least one real 0 between a and b. This makes sense the way the intermediate value theorem makes sense for us. So to show that f of x equal to x to the 5th minus x to the 3rd minus 1 has a real 0 between the x values of 1 and 2, we would need to prove the following. That first, since f of x is an odd degreed function, f of x is continuous, okay, on that closed interval between 1 and 2. We know this about fifth power functions, is that they're continuous. We didn't have a square root, we didn't have a rational, there's no point of discontinuity for that function. Second thing we need to know is what f of 1 is. If we plug in 1 to this function, 1 to the 5th power minus 1 to the 3rd power minus 1, well, that's 1 minus 1 minus 1, which is negative 1, okay? And if we evaluate f of 2, that means we're doing 2 to the 5th power minus 2 to the 3rd power minus 1, and that's 32 minus 8 minus 1, which is 23. So again, this one is negative, and this one is positive, which means at some point that graph is going to have to cross between 1 and 2. It's going to have to cross from negative 1 to 23. To get there, it's going to have to go through the x-axis. Like, that makes a lot of sense to us. So here's the proof. Here's the reason. Therefore, there exists, it's that same kind of language, there exists a value x in between 1 and 2 such that the value of evaluated at 1, f evaluated at 1 is less than 0, and f evaluated at 2 is more than 0, and that f of x is going to have to equal that sum 0 due to the intermediate value theorem. There exists some number that would become 0 for this function in between those two values, because it has to pass 0 to go from negative to positive. Like, duh, that makes sense. And that's the intermediate value theorem applied to polynomials, and that's why that was kind of stuck at the end of last lesson, is because we need that for polynomials to find zeros and prove that zeros exist between two numbers. Pretty cool stuff.